So here we are with Chapter 7, Section 2, talking about oxidation numbers. We're going to cover the definition real quick, and then we're going to look at the 8 rules we are assigning oxidation numbers. And these oxidation numbers, once you learn how to go about assigning them, they will come up later on in some future chapters. So get your definition for oxidation numbers. These right here are going to be numbers. It just shows you the distribution of electrons around bonded atoms in a molecular compound or polyatomic ion. And we'll look at both types today. You're going to notice as we go through this, these oxidation numbers look a lot like your ionic charges that we've been working with, but there are some discrepancies, and they will be shown here throughout the PowerPoint. So, rule number 1. Atoms in a pure element have an oxidation number of 0. And they give you some examples of some pure elements here. Again, make sure you write down rule number 1, everything that goes with it. And some examples are, if you pick any element off the periodic table, like you've got your sodium, potassium, boron, don't want to give a diatomic element, but we'll say argon, neon, the oxidation state is going to be 0. If you were to look at a diatomic compound like oxygen or fluorine or chlorine or nitrogen, the oxidation state is still 0. There are some allotropes out there. Here's one for phosphorus, P4, and another for sulfur, S8. Again, these are neutral compounds. They contain the same atoms of the same element, and so the oxidation state is 0. That is rule number 1. Rule number 2. See if we can go back up here. Says that the more electronegative element in a binary compound is assigned a negative number equal to the charge it would have as an ion. Likewise for the less electronegative element. So we've worked a lot with binary molecular compounds, and again, your more electronegative element, which is going to be the last element listed, will get its usual charge as an anion, but we're going to call that its oxidation number. Number 3, fluorine. Fluorine is the most electronegative element, and it has an oxidation number of -1 all of the time. So write that down for fluorine. Rule number 4, oxygen, because it's in group 16, usually has an oxidation number of -2. So most often oxygen will have an oxidation state of -2. The exceptions, and we've got a couple that we're going to look at. If oxygen is with a peroxide, such as hydrogen peroxide here, its oxidation number is -1. So I'm going to go ahead and go through this particular example with you, just showing you how to assign them. It's going to look a lot like what we did in the previous section when we were working with Roman numerals for ionic compounds, just to show you the ebb and flow of where all of these numbers go. So if I have H2O2, again, this is 2 nonmetals. You're going to learn here in the very next rule that hydrogen is always going to be a +1 unless it's with a metal. So that is our next rule. Hydrogen is a +1 unless it's with the metal. Well, hydrogen's not with the metal here, so we're going to give hydrogen its typical oxidation state of +1. As we move down, so anytime we move down, this looks the opposite of what we've done, but we are moving down, we multiply. So +1 times 2 is a +2. Since this is a neutral compound, the number that, because we're working in reverse, the number that we put underneath oxygen needs to cancel out this +2, so we're going to put a -2. And on the way up, we are dividing. So we've split this in half. That is a -2 divided by oxygen's 2, which gives us a -1. So in this case, oxygen is in its peroxide state, and it's going to be a -1. I know some holdups on people in the past have always been 2. Let's give you another compound, CO2. Well, just because it's O2 there also does not mean it's in its peroxide state. So I'm going back here. We don't have any special exceptions that you've learned about carbon till now. And the one exception you do know of, and it won't go with the next one either, but oxygen is normally a -2, unless it's a peroxide, which in this case it's not. And another exception is going to be with fluorine, and it's not with fluorine. So if I go through the same process, I have to go with oxygen in its common oxidative state of -2. When I go down, I multiply to get a -4. We want our numbers there at the bottom to cancel each other out. So below carbon, I'm going to put a +4. Now on our way up, I am dividing. So I'm working with carbon, so it's 4 divided by the understood 1 subscript for carbon, which is 4. So the oxidation state for carbon is a +4. And if you look at carbon on the periodic table, it's in group 14. We know commonly those elements can be a +4, -4, but just know their oxidation states can have a much wider range of what their options are. Again, based on the group they're in, that's just the most common for most elements what their oxidation state's going to be. So moving back on over to the next exception for oxygen, it's when oxygen is with fluorine. So we just stated in Rule 3 that fluorine is always a -1. If we work out this example, OF2, if fluorine is always a -1 oxidation state, and we run through our math, -1 times 2 is -2. We want to add to that a +2 so that those numbers at the bottom cancel. On the way up, we divide. So 2 divided by oxygen's understood subscript of 1 is a +2. So in this case, the oxidation state of oxygen is a +2. Fluorine has its typical -1. And rule number 5, hydrogen. So hydrogen is right there above group 1. Group 1's common charge is a +1, which is what hydrogen, if it's going to be with other nonmetals, that's what it's going to have. So if hydrogen is going to be with a metal, though, metals are always going to have some type of positive charge associated with them, therefore a positive oxidation state. So hydrogen will have to take on a negative oxidation state with them. A really easy example here is if we looked at, let's say, lithium hydride, LiH. Well, lithium is in group 1. Its oxidation state is always a +1. So as I move down, 1 times 1 is a +1. And there at the bottom, we need hydrogen to be a -1 to cancel out. On the way up, we divide. So -1 divided by 1 is -1. Hydrogen will be a -1 oxidation state when it's with a metal. Rule number 6. The algebraic sum of oxidation numbers of all atoms in a neutral compound is equal to 0. Up until this point, everything we did in section 1 and the examples that I have showed you so far today, when we add up those numbers at the bottom of the compound going through our math, they've all been neutral compounds, so those numbers at the bottom have to add up to be 0. Rule number 7. If you are working with a polyatomic ion, then the algebraic sum of your oxidation numbers is going to be equal to the charge of the ion. So those numbers at the bottom that you see, again, instead of them adding up to equal 0, they will equal the charge of the polyatomic ion. We will get to an example of that shortly. And rule 8. Although rules 1 through 7 apply to covalently bonded atoms, you can also use these rules with ionic compounds similarly. We've said these oxidation numbers look a whole lot like charges already. The same again is going to hold for your ionic compounds. Very similar. So let's work through this example right here. This is UF6. And with this, if I go with having to figure out, I say put a box above each of these elements so we can find the oxidation number of every element within the compound or the polyatomic ion, and then we get started. Based on the rules that we know, fluorine only has one option. Fluorine has to be a -1 because of the group it's in, and it's also the most electronegative element. So -1 times 6 is a -6. Below uranium, since this is a neutral compound, we need these numbers at the bottom to add up to be equal to 0. So we put a +6 under uranium, and on our way up, it's going to be +6 divided by uranium subscript of 1, which is 6. So your uranium is going to be a +6 oxidation state, fluorine is a -1. H2SO4 is negative. We have a lot going on in this one. So first time that we've worked with 3 different elements. H2SO4, by the way, hopefully you know the name of that, is sulfuric acid. I'm going to put a box above each of our elements and we will figure out the oxidation state. Now that you've got 3 elements, you have to go with 2 of the elements having their common charge being their common oxidation state. So with all of our rules that we have, hydrogen here is not with a metal. So hydrogen's going to have its typical +1. And then when I look at sulfur and oxygen, one of our earlier rules says the more electronegative element of the 2 will have its typical charge. The more electronegative element typically is going to be there at the end. That is oxygen, if you remember your electronegativity rules. So oxygen will carry its -2. With both of these, on the way down, we are going to multiply. So for oxygen, that's -2 times 4, which is a -8. For hydrogen, that is 1 times hydrogen subscript of 2, so that's a +2. We need all of the numbers at the bottom to add up to be equal to 0. What number needs to go under sulfur? It is a +6. +6. Now, moving our way back up, 6 divided by sulfur's understood 1 is 6. So the oxidation state of sulfur here's one of our first drastic changes, is going to be a +6. Yes, it is normally a -2 because it's in group 16, but here is an option that it has. And then we will look at a polyatomic ion, ClO3-. Hopefully you can recall the names of these just right off the top of your head. ClO3, that's an understood -1. I'm going to put a box above chlorine, a box above oxygen. Even if it were a polyatomic ion with 3 elements, you would have 3 boxes go through the same process. As I'm looking at these, chlorine and oxygen, 2 nonmetals, you have to go with your more electronegative, which is oxygen, and give it its common charge of a -2. On the way down, we multiply. -2 times 3 is a -6. This is just a little different, though, because with these numbers here, we need our numbers at the bottom to be equal to the charge of our ion, which is a -1. So this time I have to add 5 to -6 to get -1. Now we finish out our process. On the way up, we divide. 5 divided by chlorine's 1, because we're under chlorine, is a +5. Again, I know chlorine is normally a -1 because it's in group 17, but in this case, its oxidation state is +5.